These are your notes for Unit 2, Day 7 of Calculus. If you would like to see the warm-up, the homework questions we went over in class today, or the review question, just look at the finished notes. So today we're going to talk about a new rule for taking derivatives. It's called implicit differentiation. And this is when you are trying to take the derivative of a relation. So something like a circle, x squared plus y squared equals 4. So the original function, or the original equation has both x's and y's in it. And you have to take the derivative of the x's and the derivative of the y's. So we already know how to differentiate with respect to x. So if I have y is equal to x squared plus 2x plus 3, we know that the derivative of y we can write as y prime, or today we're going to write it as dy over dx. So that's the derivative of y with respect to x. So when we've been taking derivatives, we've been taking the derivative of all of them with respect to x. So this is the derivative of y with respect to x. So if we want to take the derivative of x squared, it would be 2x, and the derivative of 2x is 2, and then the derivative of 3 is 0. So the derivative of y with respect to x is 2x plus 2. With implicit differentiation, we're going to have x's and y's. But again, the whole objective is to try and find the slope of a tangent line. So we want to find the slope of this circle at any of its given tangent lines. And you probably did this activity in geometry, where you found the slope of a tangent line by using the radius, because you know that a radius and a tangent line are perpendicular to each other. But now in calculus, we can do it in a little bit more straightforward and easier fashion. So if we have the original function x squared plus y squared equals 1, and again, that's not a function, I apologize, that's a relation, it's a circle. You're going to take the derivative like you normally would of any x term. So the derivative of x squared is 2x. But when you take the derivative of a y term, you kind of think about it as chain rule. So the derivative of y's, you can kind of think of as chain rule. It's chain rule-esque. So if you were going to take the derivative of y as chain rule, the inside function would be y, and the outside function would be to the second power. So if we want to take the derivative of something to the second power, it would be 2y and then to the first power. And then after you're done, you have to take the derivative of the inside function. Well, what's the derivative of y? The derivative of y is dy over dx. So anytime you're going to take the derivative of a y function, you would take the derivative like you normally would, but then you have to multiply by the derivative of y, and the derivative of y is dy over dx. And then the derivative of 1 is 0. So once you have this, we want to know what dy over dx is equal to. So we're going to solve for dy over dx. To get the dy over dx by itself, we're going to subtract 2x from both sides. And then we have 2y times dy over dx equals negative 2x. And then divide both sides by 2y. And then the derivative of my original function is going to be negative 2x over 2y, or just negative x over y. So if I wanted to know the equation of the tangent line of this circle at any of those given points, it would just be the opposite of the x-coordinate divided by the y-coordinate. And so notice when we're going to use implicit differentiation, we need to know both the x and the y-coordinate in order to find the derivative at a given point. So again, to do implicit differentiation, you take the derivative of each term. So you're going to take the derivative of each term. And then if you take the derivative, so if you take the derivative of a y term, you need to multiply by dy over dx, because the derivative of y is dy over dx. And that's basically the rules of implicit. You're going to go through it like normal, except for if you're taking the derivative of a y term, the derivative of y itself is dy over dx, so you think of it as chain rule. So take the normal derivative and then multiply by the derivative of y, which is dy dx. So let's find the derivative of the following. So again, we take the derivatives like normal, and then if it's a y term that we're taking the derivative of, we take its derivative and then multiply by dy over dx. So the derivative of this would be 6x squared equals the derivative of 2y squared is going to be 4y to the first and then times by the derivative of y, so times by dy over dx, and then the derivative of 5 is 0. And now we're going to solve for dy over dx. So we're going to divide both sides by 4y. And so we have 6x squared over 4y, and if I reduce this, I get 3x squared over 2y is equal to dy over dx, and that would be the derivative of that relation. On the next one, 5y squared equals 2x to the third minus 5y. Well, the derivative of 5y squared is 10y dy over dx, and then the derivative of 2x to the third is 6x squared, and then the derivative of negative 5y, well, the derivative of negative 5y is negative 5, and then times the derivative of y, which is dy dx. Now I have to solve for dy dx. I'm going to add a page so I can keep going down. I need to get all my dy dx's on the same side, so I'm going to add the 5 dy over dx to the other side. And now I have 10y dy over dx plus 5 dy over dx equals 6x squared. Now notice both of those terms have a dy over dx, so I can factor out the dy over dx, and I'm left with 10y plus 5. And then we have 6x squared. Now I'm going to divide both sides by 10y plus 5. And I get my derivative, dy over dx, is going to equal 6x squared divided by 10y plus 5. And that would be the derivative of the original relation. All right, let's look at some more examples. So find the derivative of each of the following. 5x to the third minus 3xy plus 2. Well, the derivative of 5x to the third is 15x squared, and then it's going to equal. Now the next one, we've got to be careful. Negative 3xy, we have to use product rule on. So we have negative 3x times y. So remember, product rule is you take the derivative of the first function, leave the second function alone, plus you take the derivative of the second function, times leave the first function alone. So if my first function is negative 3x, the derivative of negative 3x is just negative 3, and then leave the second function alone. The second function is y. And then plus, you take the derivative of the second function, the derivative of y is dy over dx, and then times leave the first function alone, negative 3x, and then the derivative of the 2 is 0. And now again, we need to get the dy dx by itself, so I'm going to add the 3y over. And so I have 15x squared plus 3y equals negative 3x dy over dx. And then I'm going to divide both sides by negative 3x. And I get 15x squared plus 3y divided by negative 3x equals dy over dx. And if you notice, every term can be divided by 3, or you can factor out a 3 from the numerator. And if I factor out a 3 from the numerator, I get 3 times 5x squared plus y over negative 3x. And then those 3's can cancel. And so if you wanted to reduce this derivative, you would get 5x squared plus y over negative x equals the derivative dy over dx. All right, let's look at the next one. I'm going to have a product rule here. So we have negative 3x squared times y squared. And then again, we're going to have the product rule here, negative 4x times y. So the derivative of the first function would be 6x, then times leave the second function alone, so y squared, plus the derivative of y squared is 2y times dy over dx, and then times leave the first function alone, 3x squared. And then it's going to equal the derivative of 4x squared is 8x. And now we're going to use product rule again. So derivative of the first function, negative 4x, is negative 4. Leave the second function alone, which is y. And then plus the derivative of the second function is dy over dx, then times leave the first function alone, negative 4x. Now we need to get all the dy over dx's together. But I'm going to rewrite this so it looks a little bit nicer first. So 6xy squared, I can multiply those two terms. So 2y times 3x squared is 6x squared y, and then dy over dx equals 8x minus 4y, and then minus 4x dy over dx. Now I can get all my dy dx's together and all the other terms on the other side. So I'm going to add 4x dy over dx to the left side. And I'm going to subtract the 6xy squared from both sides. And now I get 6x squared y dy over dx plus 4x dy over dx equals 8x minus 4y minus 6xy squared. And now again, on the left side, I have two terms, and they both have a dy over dx, so I can factor that out. And then I have dy over dx times the quantity 6x squared y plus 4x equals 8x minus 4y minus 6xy squared. And then I can divide both sides by the 6x squared y plus 4x, and that's going to give me my derivative. So the derivative of the original relation is going to be 8x minus 4y minus 6xy squared over 6x squared y plus 4x. And if you notice, all of those terms can be divided by 2, so I could factor out a 2 from the numerator and the denominator and cancel them out, and I would have 4x minus 2y minus 3xy squared over 3x squared y plus 2x. You don't have to simplify it, but if you did, that's what it would look like. All right. What if I have implicit with some trig functions? It works the same way. So now we're going to have chain rule. So my outside function is sine, and then my inside function has product rule involved. So the inside function is 2x squared times y to the third. So chain rule says take the derivative of the outside times, leave the inside alone, 2x squared y cubed. And then for chain rule, we multiply. Now the derivative of the inside, we're going to have to use product rule. So derivative of the first would be 4x times, leave the second alone, y to the third, plus the derivative of the second would be 3y squared dy dx, and then times, leave the first function alone, 2x squared. So that would be the derivative of the left side. So cosine x 2x squared y cubed times 4xy to the third plus 3y squared dy dx 2x squared. And then equals the derivative of the right side would be 9x squared plus 0. I'm going to make this look a little bit nicer. So that would be the cosine of 2x squared y to the third times 4xy to the third. And now I can multiply the 3y squared and the 2x squared together. So plus 6x squared y squared dy over dx equals 9x squared. Now I need to get the dy dx by itself, so I'm going to divide both sides by this cosine. So cosine 2x squared y to the third, divide by cosine 2x squared y to the third. And now I have 4xy to the third plus 6xy squared times dy dx equals 9x squared over the cosine of 2x squared y to the third. Now I need to get the dy dx by itself, so I'm going to subtract the 4xy to the third from both sides. And then I get 6x squared y squared dy dx equals 9x squared over cosine 2x squared y to the third minus 4xy to the third. And then my last step is I'm going to divide both sides by 6x squared y squared, and I'm going to leave it looking ugly. So dy dx is going to equal 9x squared over cosine 2x squared y to the third minus 4xy to the third, and then all of that divided by 6x squared y squared. And I'm going to leave it unsimplified as a complex fraction. All right. So what if we actually want to find the slope of a graph using implicit differentiation? So let's start with x squared plus y squared equals 1. And let's say I want to know what the slope of this line is at the point 1, 0. So what would be the slope of this graph at the point 1, 0? Well, first, let's find its derivative. So derivative of 2x, or x squared would be 2x, and then the derivative of y squared would be 2y dy dx, and the derivative of 1 is 0. If I solve for dy dx, subtract the 2x, subtract the 2x, and 2y dy dx equals negative 2x. Divide both sides by 2y, and then the slope of the tangent line, or the derivative, is going to equal negative 2x over 2y, or negative x over y. And then if I wanted to know the derivative at the point 1, 0, I'd take 1 and 0 and plug it in. So proper notation, you would do dx dy at the point 1, 0. So you draw like a straight bar down and then put the 1, 0 down at the bottom. It's going to equal negative 1 over 0. Well, that's undefined. So the derivative doesn't exist at the point 1, 0. Does that make sense? Well, this is a circle with the center at 0, 0. And then its radius is 1. So we would go up 1 over 1. And at the point 1, 0, we're right here. And if I drew in a tangent line, it'd be a vertical line. And the slope of a vertical line doesn't exist. So it looks like we did that right. What about if we want to write the equation of a tangent line at the point 2, 1? So the equation of a tangent line, remember we can use point slope form, y minus y1 equals m times x minus x1. So to find m, it's going to be the derivative at the point 2, 1. So we've got to find the derivative and plug in 2, 1. So I'm going to use product rule because it's x squared times y. So the derivative of the first is 2x times, leave the second alone. So 2x times y plus the derivative of the second is dy dx times, leave the first alone, x squared equals the derivative of x is 1 and the derivative of 2 is 0. I want to get the dy dx by itself, so I'm going to subtract 2xy from both sides. So I have dy dx times x squared equals 1 minus 2xy. And then I'm going to divide both sides by x squared. And so the slope of my tangent line at any point is going to be dy over dx is equal to 1 minus 2xy over x squared. But now I want to find that at the point 2, 1. So I'm going to plug in 2 for x and 1 for y. So this is going to be 1 minus 2 times 1 over 2 squared. And so this is going to be 1 minus 4, which is negative 3, and then over 2 squared is 4. So the slope of my tangent line is going to be negative 3/4. So now the equation for my tangent line is going to be y minus y1. And we have x1 and y1 right here. So y minus 1 equals negative 3/4 times x minus x1, so x minus 2. And that would be the equation of my tangent line at the point 2, 1 for that relation. Let's look at the next one. X squared y squared plus x squared y equals 2. So again, for both of these, we're going to have to use product rule. So x times y squared and x squared times y. So the derivative of x is 1, then times, leave the second alone, y squared, plus the derivative of y squared is 2y dy dx, and then times, leave the first alone, x. And then plus, now we're going on to the second function, x squared y. So the derivative of x squared is 2x times y, plus the derivative of y is dy dx, times the first function, x squared, and then equals the derivative of 2 is 0. So we have y squared plus 2xy, just multiplying those pieces together, dy dx, then plus 2xy, then plus x squared dy dx equals 0. I need to get all of the dy dx's together, and then I'm going to move everybody else to the other side. So I'm going to minus y squared, and I'm going to minus 2xy from both sides. Add a page. And I get 2xy dy dx plus x squared dy dx equals negative y squared minus 2xy. Factor out a dy dx from the left side, and we have 2x plus x squared. And then equals negative y squared minus 2xy. And then to solve for dy dx, we're going to divide both sides by the 2xy x squared, 2xy plus x squared. And then we have the slope of the tangent line, or the derivative anywhere on this relation, is going to be negative y squared minus 2xy over 2xy plus x squared. But we want to find it at the point 1, negative 2. So the derivative of this function at the point 1, negative 2 is going to be plug in 1 for x and negative 2 for y. So it would be negative times negative 2 squared minus 2 times 1 times negative 2 all over 2 times 1 times negative 2 plus 1 squared. And so this would be exponents first. Negative 2 squared is 4, and then the opposite of that is negative 4. And then negative 2 times 1 times negative 2 is positive 4. And then all over negative 4 plus 1, this is going to be 0. So the slope of the tangent line at the point 1, negative 2 looks to be 0. And so the equation for the tangent line is going to be y plus 2 equals 0 times x minus 1, or y equals negative 2, if you simplified that all the way down. For implicit differentiation, you can also find the second derivative. These are a little bit interesting because once you find the first derivative, you take the derivative of that. But within the derivative of the second derivative, or with the second derivative, it's going to have the first derivative as part of it. What do I mean by that? Well, let's check it out. So x squared plus y squared equals 1. The derivative of x squared is 2x. The derivative of y squared is 2y. dy dx, the derivative of 1 is 0, and the derivative of 0 is 0. So if we're going to solve, we're going to subtract the 2x over, and we get 2y dy dx equals negative 2x, divide by 2y, And dy dx is going to equal negative x over y. So that's going to be my first derivative. And then if I want to find the second derivative, which is d2y over dx2, I take the derivative of the first derivative. Okay, well, to take this guy's derivative, I'm going to have to use quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So d2y over dx2 is going to equal, the derivative of the top is negative 1 times the bottom minus the derivative of the bottom is dy dx times the top all over the bottom squared. And so this is going to be negative y plus x dy dx over y squared. And that's my second derivative. But notice within the second derivative, I have a dy dx. So I need to be able to substitute what dy dx was into that. Well, dy dx is equal to negative x over y. So I'm going to take the negative x over y and substitute it in right there. And so my final second derivative is going to be negative y plus x times negative x over y all over y squared. And that's going to be the second derivative for the original relation x squared plus y squared plus 1 equals 0. All right, let's look at the next one. 5 equals 4x squared plus 5y squared. So if I take the derivative of this, I would get 0 equals 8x plus 10y dy dx. And if I solve for dy dx, I get negative 8x equals 10y dy dx. Divide by 10y, and negative x over 10y, which is equal to negative 4x over 5y, is the first derivative dy dx. To find the second derivative, d2y over dx squared is going to equal, dx2, is going to equal quotient rule. Derivative of the top is negative 4 times, leave the bottom alone, minus derivative of the bottom is 5 dy dx times, leave the top alone, negative 4x, then all over the bottom squared, so 5y squared. So if I simplify this, I get negative 20y plus 20x dy dx all over 25y squared. And now notice we have another dy dx, so I need to substitute what dy dx was, and dy dx was negative 4x over 5y. So I'm going to take that and substitute it in. And so my final second derivative is going to equal negative 20y plus 20x times negative 4x over 5y all over 25y squared. And that would be the second derivative using implicit differentiation. Your homework is the